Hello there, and welcome back to Fall Asleep to Astronomy. I'm glad you've wandered into this little corner of the night with me. Out beyond the quiet of your room, the universe is still awake, stars humming softly, planets turning, and somewhere, perhaps, other skies with their own questions. Tonight, we'll drift toward one of the most tender possibilities we have ever imagined, that we might soon learn we are not alone. We'll listen to the faint hints scientists are tracing in starlight and distant worlds, and follow the gentle threads that suggest other places may cradle life of their own. There is no rush here, only slow wonder, shared in a low voice meant for late hours. If this kind of soft, stargazing company feels right to you, a quiet like and a gentle subscribe help others find their way here too. For now, let the night be spacious, and we'll wander outward together. Far out in the cold light of Jupiter, there is a small world that keeps a very large secret. Europa, one of Jupiter's many moons, looks quiet and still from far away, like a smooth marble of ice drifting in the dark. But beneath that frozen shell, hidden under kilometers of ice, lies something astonishing. A global ocean, wrapped all the way around the moon, sealed away in darkness for a time longer than all of human history. Many scientists believe that this ocean may not be empty. It may be stirring, churning, and quietly carrying the ingredients that life loves most. To reach a place like that, to listen to the whispers of an ocean that has never seen the sun, we need more than curiosity. We need a patient machine willing to cross the vastness between worlds. That is what NASA's Europa Clipper is meant to be. It is one of the most ambitious explorations ever planned. A robotic traveler built specifically to study whether an icy moon like Europa could be a home for life. The spacecraft was launched in October of the year 2024, leaving Earth with a simple but profound question folded into its journey. Could this distant ocean support something alive, even if that life is small and fragile and nothing like us? Europa Clipper is not heading straight into a landing. Instead, it is taking the long, careful route, winding its way through the inner solar system, building up speed from gravity and patience. In the distant 2030s, when it finally settles into Jupiter's neighborhood, it will not hug Europa closely. Instead, it will loop through Jupiter's orbit and then, again and again, swoop in for close passes. Each flyby will be like brushing fingertips across the surface of a secret, collecting tiny fragments of information about what lies inside. During these many passes, Europa Clipper will study the moon's icy shell, the invisible ocean beneath, and the delicate boundary between them. It will measure how thick the ice might be, how salty the water may feel, and whether there is energy moving through that hidden sea energy that could keep it warm, mixed, and welcoming to chemistry that resembles life's first steps. For the first time, a spacecraft's main purpose is to ask whether a distant ocean world is truly habitable, not just interesting, not just beautiful, but capable of supporting life as we understand it. Life that needs liquid water, a steady source of energy, and the right blend of chemical ingredients. From the outside, Europa looks harsh and uninviting. Its surface is a hard, pale crust of ice, scarred with cracks, ridges, and stains where material from below seems to have pushed upward. It is bitterly cold out there, and the moon lies deep in Jupiter's violent radiation field. To human eyes, it might seem like the last place life would choose, yet just under that frozen shell may be one of the most promising environments beyond Earth for anything living. The ocean beneath is thought to be global and deep, possibly holding more water than all of Earth's oceans combined, and then some. The thick ice acts as a shield, blocking much of the harmful radiation from above, while the moon's dance around Jupiter creates tides that knead and flex its interior, gently heating it from within and keeping the ocean in a liquid state. Inside Europa Clipper, a collection of carefully crafted instruments waits like a set of senses tuned to ice, rock, and water. One of the most important is an ice-penetrating radar, which sends gentle pulses down through the frozen shell and listens for echoes returning from different depths. From the timing and strength of those echoes, scientists can estimate how thick the ice is and whether there are places where the ocean and the surface might touch or exchange material. Those contact points could be crucial because they might allow chemicals from the surface to sink into the ocean and material from the ocean to rise, creating circulation that life could use. Other instruments act like eyes that can see what our eyes cannot. Spectrometers aboard the spacecraft will look at the light reflected from Europa's surface and break it into its component colors, the way a prism spreads sunlight into a rainbow. Hidden in those patterns of color are fingerprints of different substances: frozen water, salts, simple organic molecules, maybe even more complex compounds. By studying these patterns, scientists hope to understand what kinds of chemistry are happening on the surface and whether any of it hints at processes that life might favor. Europa Clipper will also carry magnetometers, instruments that measure the moon's magnetic environment. Europa moves through Jupiter's strong magnetic field, and the salty ocean inside the moon can conduct electricity, creating its own subtle response. By tracing how the magnetic field shifts and twists as the spacecraft flies by, these instruments can help estimate how deep the ocean lies and how salty it is. A saltier ocean conducts better, and that conductivity changes the magnetic signature in a way that can be measured from afar. Piece by piece, flyby by flyby, the spacecraft will turn invisible structures into knowable shapes. With each pass, Europa Clipper will refine our picture of the ice shell, the ocean below, and any hydrothermal activity that could be happening on the seafloor. On Earth, in the darkest parts of our deepest oceans, hydrothermal vents spew hot, mineral-rich water into the cold depths. Around these vents, life flourishes without sunlight, feeding on chemical energy instead. If something similar exists on Europa's ocean floor, warm vents, mineral-rich plumes, rocky surfaces for chemistry to cling to, then this quiet moon could host a kind of ecosystem powered not by starlight, but by the inner warmth of a restless world. All of this careful exploration, however, must take place in one of the harshest radiation environments in the solar system. Jupiter's magnetic field is enormous, many thousands of times stronger than Earth's, and it traps swarms of charged particles that race around the planet at incredible speeds. Close to Jupiter, these particles create a storm of ionizing radiation, an invisible blizzard that constantly bombards the surrounding space and the moons held in that grip, including Europa. For a delicate spacecraft packed with sensitive electronics, this is not just an inconvenience, it is a serious threat. For Europa Clipper, survival is as much an engineering challenge as a scientific one. The spacecraft's heart, its computers, memory, and communication systems must function in a place where individual particles can slam into circuits and quietly damage them. To protect these fragile systems, engineers have placed the most important electronics inside a heavily shielded vault, a kind of metal safe within the spacecraft. This vault is made from layers of materials like aluminum and zinc, chosen for their ability to absorb and scatter incoming radiation, reducing the amount that reaches the circuits inside. Even with this protective shell, the environment around Jupiter is so intense that some damage is expected over time, the smallest and most numerous elements of the spacecraft's electronics, its transistors, are especially vulnerable. Many of these transistors are of a type called metal oxide semiconductor field effect transistors, often shortened to MOSFETs. They are the tiny switches that guide the flow of electricity through the instruments and control systems, turning signals on and off, shaping data, and helping the spacecraft think and respond. Ionizing radiation can quietly alter the delicate layers inside these switches, changing the way they behave. A transistor that once turned off cleanly might begin to leak, or one that should switch on at a certain voltage might drift away from that point. Recent ground tests have suggested that some of the transistors planned for use on Europa Clipper may begin to fail at lower radiation doses than first hoped. That does not mean the mission is doomed, but it does mean the engineers must look closely at the risks and decide how to live with them. Because the electronics vault was sealed in the year 2023, swapping out the hardware would mean opening the vault, rebuilding, and delaying the mission significantly. Instead, the team has spent months carefully weighing two heavy choices: accept the known vulnerabilities and rely on clever operations and built-in backups, or reopen the vault, replace parts, and accept the cost in both money and time. It is a quiet, high-stakes balancing act, with the future of the mission resting on how much risk is reasonable in pursuit of such a rare opportunity. Designers did not assume everything would work perfectly forever. Europa Clipper carries redundancies backup systems that can take over if some components weaken or fail. Software can be updated to avoid the highest radiation zones when possible, or to lean more on instruments and circuits that remain healthy. The mission team has explored strategies like adjusting how often certain instruments are used in the harshest regions, or rerouting tasks to different parts of the spacecraft's electronic brain. The aim is not to avoid all damage that would be impossible, but to ensure that any damage that does occur does not block the central goal: understanding Europa's ice, its ocean, and whether that secret sea might truly be habitable. While Europa Clipper concentrates on Europa, it is part of a wider story about icy moons with hidden oceans. Saturn's tiny moon, Enceladus, for example, also seems to hide a global sea beneath its surface, and it even sprays plumes of water vapor and ice out into space like a fountain, giving passing spacecraft a direct taste of its interior. Together, these worlds are expanding our imagination of where life could exist. Instead of looking only at rocky planets in the warm zone of their stars, we are learning to pay attention to frozen shells with warm hearts, where tidal forces from giant parent planets keep deep oceans from freezing solid. These oceans share three crucial qualities that make scientists' hearts quietly hopeful: liquid water, energy sources, and essential chemical elements. The tidal push and pull from their parent planets keep the water moving and may drive hydrothermal activity at the seafloor. Rock and water can then interact, releasing minerals and chemical energy. And within the water itself, elements like carbon, hydrogen, nitrogen, and oxygen can blend into countless combinations. On Earth, such combinations once formed the first fragile chains and structures we call life. Still, having the right ingredients is not the same as knowing how they are stirred or whether they are delivered in the right amounts. One key question is how elements such as oxygen, which many familiar forms of life depend on, find their way into these buried oceans. In a world where sunlight barely reaches the surface and never touches the water directly, oxygen must be produced and transported in other ways. Understanding that subtle journey is one of the quiet puzzles scientists hope to solve. Europa offers an intriguing clue. The same radiation that threatens spacecraft might also act as a strange kind of chemistry engine on the moon's surface. As Jupiter's high-energy particles crash into the icy crust, they can break apart simple water molecules into lighter hydrogen and heavier oxygen. The hydrogen, being small and energetic, often escapes into space, lost to the vacuum. The oxygen, however, has a different fate. Some of it lingers near the moon, contributing to a thin, ghost-like atmosphere. Some of it may become trapped in the ice itself, and some is thought to sink slowly downward. Cracks in the ice, regions where it has fractured or melted and refrozen, may act as gentle pathways. Salty channels and pockets of brine can connect the surface to deeper layers, allowing oxygen and other reactive chemicals created by radiation to drift or be carried toward the ocean below. Over long spans of time, this steady trickle could deliver a meaningful amount of oxidants into the water, offering potential food for any microscopic life that might exist there, the way oxygen and other compounds support ecosystems in Earth's seas. In current theories, this process radiation breaking water apart at the surface, with oxygen gradually migrating downward through the cracked and briny ice, is considered one of the main ways that oxygen could enter Europa's hidden ocean. Even with all this quiet machinery of chemistry at work on Europa's surface, the story of oxygen there has turned out to be gentler and more restrained than many once imagined. For years, rough calculations suggested that the moon might be producing enormous amounts of molecular oxygen, enough to flood its hidden ocean with oxidants in great abundance. But more recent studies, especially those informed by careful measurements from NASA's Juno spacecraft as it glided through Jupiter's realm, have painted a softer, more conservative picture. The glow of oxygen around Europa seems fainter than expected, its presence more like a thin whisper than a roar. From these newer observations, scientists now estimate that Europa produces on the order of 26 pounds of molecular oxygen every second. That is still a remarkable amount, but it is far below the earlier guesses that reached as high as 2,000 pounds per second. The difference between those numbers is not just a matter of pride for modelers. It reshapes how we think about the chemistry of the moon's ocean. With less oxygen being made at the surface, less can slowly seep inward through the ice. That means the supply reaching the subsurface water might be more limited than once hoped, narrowing the range of conditions under which familiar, oxygen-hungry life could comfortably exist. This does not close the door on life. It simply changes the kind of life that feels most plausible. Even at these lower production rates, Europa may still create enough oxygen and enough chemical energy in general to sustain living systems that are frugal and efficient. Instead of vast, oxygen-rich seas like Earth's shallow coastal waters, one might imagine a quieter world where life survives on thinner margins, using every bit of available energy with exquisite care. The way oxygen and other oxidants drift downward through cracks and briny channels could still set up subtle chemical gradients that living cells, if they exist, might learn to tap. The picture that emerges is one where potential life does not bask under sunlight, but huddles in dark, chemically rich oases, not so different from some of the strangest places in Earth's own oceans. On our planet, in the lightless depths far below the reach of day, we have found ecosystems that do not depend on photosynthesis at all. Instead, they live on chemosynthesis, life fueled not by the energy of photons, but by the energy locked in molecules and minerals. At the bases of these communities are microbes that use chemical reactions between water and rock to build organic matter, becoming food for larger creatures in a chain that never sees the sun. Many astrobiologists look at Europa's hidden ocean and think of these earthly analogs. They picture hydrothermal vents on the seafloor, places where warmed, mineral-rich water seeps or gushes out of the rock into the colder ocean around it. On Earth, the vents can form towering chimneys that billow dark, hot fluid, earning names like black smokers. Around them cluster lush forests of tube worms, strange crabs, and other extremophiles built to withstand crushing pressure and high temperatures. The heat that drives these vents comes from Earth's molten interior, where magma and hot rock provide an almost inexhaustible source of energy. Europa and Saturn's moon Enceladus are different. As far as we can tell, they do not have the same kind of large, molten core that Earth does. This absence raises an important question. Without that deep reservoir of molten rock, can strong, high-temperature hydrothermal systems really persist? The answer, according to new models, may be yes, but in a quieter, cooler form. Instead of roaring black smokers with temperatures climbing to more than 700 degrees Fahrenheit, the vents on these icy moons are expected to be milder, with lower temperatures yet still warm compared to the surrounding ocean. These low-temperature hydrothermal systems might be gentle, but they could also be long-lived. Tidal flexing from the parent planet can keep rocks slowly cracking and grinding, allowing water to percolate through. Over billions of years, that constant kneading could maintain modest but steady amounts of heat. The result would be a network of cooler vents that nonetheless provide a stable source of warmth and chemical disequilibrium. Exactly the kind of environment that chemosynthetic life loves. In this view, Europa's seafloor becomes less like a dramatic volcanic battlefield and more like a vast, ancient workshop where rock and water meet in countless small reactions. We see hints of this kind of process in places on Earth where hydrothermal activity is quieter. Along the Juan de Fuca Ridge in the Pacific Ocean, for example, cold seawater sinks down into the ocean crust through cracks and pores in the seafloor. As it descends, it winds its way through old volcanic rocks, absorbing heat slowly. By the time it rises again through vents and fissures, it is no longer icy, but gently warmed and chemically transformed. Minerals from the crust leach into the water, enriching it with substances like hydrogen sulfide and methane that can power chemosynthesis. Around these vents, life flourishes in forms specially adapted to those conditions. Delicate tube worms anchor themselves near the flow, hosting symbiotic bacteria inside their bodies that perform chemosynthesis on their behalf. Other extremophiles, from microbes to more complex creatures, cluster in the surrounding area, each one tuned to a narrow band of conditions that would be lethal to most surface animals. They are living proof that life can take root and thrive in environments that would seem utterly hostile if judged by the standards of a sunny shoreline or a forest glade. If something similar exists on Europa, then its ocean floor may be dotted with sites where water and rock quietly collaborate to produce energy. Any life there would likely be microbial at first glance, small and humble, yet in its own way, it would be as astonishing as the first tube worms discovered at Earth's vents, showing that biology can write its story in places that never see starlight. The oxygen trickling down from the ice above, combined with reduced compounds rising from the rock below, could set up a delicate energy circuit that sustains such organisms over immense spans of time. While much of this remains in the realm of careful inference, Europa's surface itself keeps offering clues that something dynamic is happening below. One of the most striking signs comes in the form of water plumes, jets of vapor that appear to erupt from cracks in the icy shell, reaching out into space like brief, ghostly fountains. These plumes were first hinted at in observations from the Hubble Space Telescope which detected subtle signatures of water vapor near the moon. More recently, additional missions, including Juno, have lent weight to the idea that Europa occasionally sprays material from its interior into the surrounding vacuum. When Juno passed close to Europa in the year 2022, its instruments captured high-resolution images that revealed a surface far from simple. Instead of a smooth, unbroken crust, the landscape is carved with ridges, crisscrossed fractures, and chaotic regions where blocks of ice seem to have broken, shifted, and frozen into new, disordered arrangements. Among these complex features are areas that scientists think may be the sources of water vapor plumes, where cracks reach deep enough for liquid from the subsurface ocean, or pockets of brine to find an escape route. The jets themselves are thought to rise astonishing distances, up to around 120 miles above the surface, before falling back or drifting away. In the near vacuum of space, salty liquid that squeezes its way through a fissure can flash into vapor almost instantly, carrying with it tiny ice grains and dissolved substances from the interior. Each plume becomes a brief, natural sampler, taking a little piece of the hidden ocean and throwing it into a place where passing spacecraft can reach it. For explorers, this is an extraordinary gift. Instead of drilling through an unknown thickness of ice, a task that would require huge amounts of energy and years of effort, a spacecraft can simply fly through a plume and extend its instruments like cupped hands. Mass spectrometers can sniff the vapor, separating its components and weighing individual molecules. Dust analyzers can catch and examine tiny grains of ice and salt. In these droplets and particles, scientists hope to read the chemical story of Europa's ocean directly, rather than only inferring it from afar. The expelled material is expected to contain water and salts at the very least, but the real excitement lies in the possibility of more complex ingredients. If molecules such as methane, simple organic compounds, or even amino acids are detected, it would be a strong sign that the ocean hosts rich chemistry that could feed or accompany life. The ratio of different substances can hint at whether the ocean is interacting with a rocky seafloor, which is crucial for generating the chemical gradients used in chemosynthesis. The salinity of the water, too, and the presence of certain ions can tell us whether the ocean is more like a mild terrestrial sea or something far more exotic. By carefully studying the chemistry of these plumes, scientists can begin to answer layered questions about habitability. Do we see the oxidants that would serve as food for microbes? Are there reduced compounds, such as hydrogen or methane, that could be paired with those oxidants in energy-yielding reactions? Does the balance of elements like carbon, nitrogen, and oxygen resemble environments on Earth where life thrives, or does it push us into less familiar territory? Every fly-through, every measured plume adds another thread to the tapestry of understanding. Europa's surface holds other hints as well, in the shapes and scars etched into its ice. One particularly intriguing region has been nicknamed the Platypus, a patch of chaotic terrain that stands out in Juno's images. Instead of smooth plains, this area is made of jumbled ice blocks, ridges, and disrupted patterns, as though the crust has been broken apart, stirred, and refrozen. The feature spans roughly 23 by 42 miles, making it large enough to hold entire cities if it were transplanted onto Earth, and yet it is just one patch on a world full of such complexities. The appearance of the platypus suggests it is geologically young, at least in the slow timescales of the outer solar system. Ice there seems to have been moved and rearranged relatively recently, hinting that liquid water or soft, warm ice may have come close to the surface, weakening and deforming the crust. Salty water could have seeped upward, altering the texture and structure of the ice before freezing again. Patterns like this tell scientists that Europa is not a static, frozen relic, but a changing world with an active interior. Across the moon, Europa's outer shell is believed to be divided into large, rigid plates of ice floating on top of the underlying ocean. Under the influence of Jupiter's powerful gravity, these plates can move, flex, and occasionally collide in a way that faintly echoes Earth's tectonic plates. As they shift, they create fractures, ridges, and zones of chaotic terrain, like the platypus, and these surface deformations may in turn affect how material is exchanged between the ocean and the ice above it. Where plates stretch apart, new cracks can open. Where they converge, blocks can tilt and stack, forming complex patterns. Careful analysis of Juno's images of the platypus region has revealed a remarkably detailed arrangement of ice blocks, some of them up to about 1 kilometer across. The blocks are separated by networks of cracks and gaps, suggesting that the plate segments do not sit perfectly still, but may slide, rotate, or drift relative to one another over time. This patchwork, with its shuffled pieces and visible seams, offers a direct glimpse of how Europa's frozen skin responds to the forces acting upon it. It is thought that this restless, ever so slow motion is driven by the constant tidal flexing Europa experiences as it orbits Jupiter. As those great slabs of ice on Europa's surface drift, tug, and fracture, they do more than redraw patterns of ridges and blocks. Each crack and separation may open a pathway, a narrow corridor reaching down toward the hidden sea below. In some places, scientists suspect that water from the subsurface ocean is able to creep upward along these fractures, seep to the surface, and then freeze in place. As it rises, it can carry salts and other materials with it, leaving behind darker, low-albedo patches on the ice stains that may be quiet signatures of salty liquid once emerging from the depths. When researchers compare Juno's sharp new views of regions like the platypus with older images from the Galileo spacecraft, they notice subtle differences that hint at change over time. In some Juno images, the southern part of the platypus appears slightly broader, and certain ice blocks beneath the eye shape seem to have a different outline or texture than before. The variations could be due, in part, to differences in lighting and image quality, but they may also be gentle signs that Europa's face is still evolving. If even small shifts have occurred between the Galileo era and Juno's recent flyby, that would suggest ongoing geological activity, ice plates that continue to move, melt in places, and refreeze as salty water rises and reforms the surface. These interactions between ice plates are far from mere curiosities. Where plates pull apart or grind past each other, friction and tidal flexing can produce localized heating. In those warm pockets, ice may soften or melt, and briny water can find its way upward. As that water reaches colder layers, it freezes again, building new surface textures, ridges, hummocks, and chaotic patches that tell the story of motion below. Understanding these processes is essential because they also hint at how we might someday access material from the ocean without having to bore through the entire thickness of Europa's shell. If fractures and openings regularly connect surface and interior, then frozen samples of ocean water could be collected at or near the surface, like messages from the deep carried up by the moon itself. This is one of the reasons Europa and Saturn's little moon Enceladus feel so special in the quiet catalog of the solar system. Among all the worlds we know, these two icy moons stand out as some of the most promising places to look for life beyond Earth. both hide global oceans beneath their frozen exteriors. Both sit within strong gravitational fields that knead their interiors, likely driving hydrothermal activity, and both appear to send pieces of their inner oceans outward in ways we can study. One of the clearest potential signs of habitability on these moons comes from the water vapor plumes that erupt from their surfaces. On Enceladus, spectacular geysers blast out from fractures near the South Pole, shooting jets of water, salts, and organic compounds hundreds of miles into space. These geysers are firm, direct evidence that a liquid water ocean exists beneath the ice, and that it is in contact with a rocky core, a crucial requirement for the kinds of rock-water reactions that feed chemosynthetic life. Europa's plumes, by contrast, have been more elusive, more like hints than declarations. Indirect observations suggest that similar jets may occasionally burst through cracks in its ice, though they may be weaker or less frequent than those on Enceladus. Even so, the possibility that Europa sometimes vents water vapor into space is enormously important. Both moons are thought to host hydrothermal systems deep in their oceans, where heat and chemical energy are generated as water interacts with warm rock and minerals. On Earth, these deep-sea environments teem with life. Despite the total absence of sunlight, if comparable conditions exist on Europa or Enceladus, they could support microbial ecosystems hidden far beneath the ice. Enceladus has a small advantage when it comes to ease of access. Its plumes are strong and continuous enough that previous missions have already flown through them and directly sampled their contents. By tasting the spray, so to speak, spacecraft can study the chemistry of the ocean without any drilling at all. Europa, with its thicker and perhaps more rigid ice shell, may be concealing more complex, long-term interactions between surface and sea. The pathways for exchange might be slower, the history richer and more intricate. That complexity makes Europa no less fascinating. If anything, it deepens the allure of what might be happening in its buried waters. Against this backdrop, the Europa Clipper mission, launched in October, becomes a delicate key to a locked and distant door. Although the spacecraft will not touch down on Europa's surface, it will perform roughly 50 close flybys, each one an intimate glance that adds to a growing picture. During these passes, its instruments will map the ice, measure its thickness, probe the structure of the ocean beneath, and analyze the chemistry of both surface material and any plumes that can be sampled. With each loop, Europa will reveal a little more of itself. The signs of life that Europa, Clipper, and future missions are searching for are not likely to be obvious fossils or complex organisms. Instead, they will be subtle chemical fingerprints, clues woven into the ice and vapor. If amino acids, simple organic molecules, or other biochemical building blocks are found in the plumes or near-surface ice, it would be a powerful hint that the oceans of these moons are not merely wet, but chemically active in ways that life could exploit. Recent studies suggest that, on Enceladus, such biosignatures might be preserved at relatively shallow depths, protected within surface deposits of plume material. This raises the possibility that a future lander might dig only a short way into the ground to reach meaningful samples. Europa poses a greater challenge. Its thicker ice shell and intense radiation environment make it harder for fragile molecules like amino acids to survive near the very surface. However, modeling work has suggested that beneath a modest depth, especially in regions shielded from the harshest radiation, there could still be preserved signatures of organic chemistry. In those protected layers, delicate molecules may endure for long periods, waiting to be found by the right instruments. Active regions associated with plumes or chaotic terrain might be particularly promising, as fresh material from the interior could be deposited and then quickly buried, sheltered from energetic particles. In this sense, Europa Clipper is not just a mission of immediate discovery, but also a scout for future explorers that may land and dig. The data it returns will help identify the safest and most scientifically rich places to touch down, sample ice, and perhaps even capture newly fallen plume material. A future lander could melt or drill a short way into the crust, analyze the trapped chemicals, and search more directly for patterns that resemble metabolism or prebiotic chemistry. The dream is not only to confirm that the ocean exists and is salty and deep, but to begin answering whether it has ever been home to something living. Europa Clipper has already left Earth behind, carrying these hopes into the dark. The stakes feel quietly enormous. Whatever it finds will reshape our understanding not only of this single moon, but of icy ocean worlds as a whole. Its strategies, flying repeated close passes instead of landing immediately, using a suite of remote sensing tools and plume sampling techniques, will likely become a template for missions to other frozen moons that may hide seas of their own. Each measurement nudges open the door to a larger realization that habitable environments might be far more common than the narrow band of warm, rocky worlds we once imagined. And yet, the questions about life do not belong only to distant spheres. While we look outward toward hidden oceans under alien ice, there is another story that pulls us back toward our own world, to a time when Earth itself wore a very different face. Imagine standing on a planet where the seas have turned to solid glass, where ice stretches uninterrupted from pole to pole, and where even the equator, usually a symbol of warmth and vibrancy, is smothered in frozen stillness. Glaciers tower where forests once grew, and the familiar blues and greens of Earth are replaced by a stark, blinding white. It sounds like a bleak scene from a distant, lifeless world. But this vision is rooted in our planet's own deep past. This is the puzzle of an almost entirely ice-covered Earth, a mystery that scientists are still gently unraveling. You might think of a bad winter as something that passes in months, or a harsh ice age as a pattern that lasts tens of thousands of years. But imagine a winter that lingers not just for centuries or millennia, but for around 100 million years. The thought stretches the mind, and it stretches our understanding of how a planet with oceans, continents, and living things could slip into such a deep freeze and, even more importantly, how it could ever emerge again. These questions pull at the edges of what we know about climate. They ask how delicate the balance truly is between warmth and cold, between open water and locked ice. They suggest that Earth's climate system, while resilient, is capable of swinging into states that are far beyond the familiar rhythms of ice ages and interglacial warmth. To follow this story, it helps to remember that our planet has been journeying through space for about 4.2 billion years, wearing many different faces along the way. In its earliest times, during what is sometimes called the Hadean Eon, Earth was a world of intense heat and chaos, with molten rock at the surface and frequent impacts from space. Much later, during the Cambrian period, warm tropical seas cradled an explosion of new forms of life. As complex animals appeared in abundance, in the Mesozoic era, dinosaurs roamed lush landscapes under generally warmer conditions than today, and in other periods, such as parts of the Permian, ice and cold advanced, and the planet wrestled with widespread glaciation. You might wonder if all of these shifts are simply part of a natural, gentle cycle, like a slow pendulum swinging between warmer and cooler states. In many ways, they are. Earth has repeatedly moved between ice ages and warmer interglacial periods, guided by a blend of influences: variations in the amount of sunlight reaching different latitudes, changes in greenhouse gas levels, shifting ocean currents, the arrangement of continents, and many other factors. These cycles give our climate a kind of heartbeat, a rhythm that plays out over tens of thousands to millions of years. Yet the idea of a planet locked in ice for around 100 million years stands apart from those familiar patterns. It is not merely a deeper dip in the usual swing. It looks more like a step into an entirely different state. Equatorial regions, which normally host rainforests and warm seas teeming with life, are instead imagined as expanses of frozen rock and ice, quiet and windswept. This scenario is sometimes called a snowball Earth, and it feels like an extreme outlier, an anomaly that begs for explanation. The more scientists study this possibility, the clearer it becomes that such a global freeze is not just another chapter in the regular cycle of ice ages. It is a climatic event of extraordinary magnitude, so severe and so all-encompassing that it challenges our understanding of how Earth's natural systems are supposed to behave. To unravel a mystery as deep as a frozen Earth, scientists turn to some of the quietest storytellers we have: rocks. Layers of stone are like pages in a history book, each one preserving traces of climates long gone. When geologists read those layers, they are listening to a planet remembering itself. One of the most haunting clues is something called a dropstone. Picture a glacier extending out over an ancient sea, carrying pebbles and boulders frozen into its ice. As chunks of that ice break off and drift as icebergs, they slowly melt, letting the stones fall and plunge into the soft mud on the seafloor. Millions of years later, that mud hardens into rock. When we cut into it, we sometimes find large, lonely stones sitting inside fine, oceanic sediments where they clearly do not belong. What makes these drop stones remarkable is where they are found: in rocks that formed near ancient tropical regions, even in what are now vast deserts. Their presence is like a soft-spoken confession that ice once reached latitudes we usually imagine as warm and inviting. They suggest a time when glaciers and floating ice were not confined to the poles but extended far into low latitudes, scattering their rocky cargo into seas that should have been ice-free. Ice itself holds another part of the story. From the great polar sheets, scientists drill out ice cores, long cylinders reaching down through layers that built up year after year as snow fell and compressed. Trapped within the ice are minuscule bubbles of ancient air, sealed away when the snow first settled. By studying these bubbles, researchers can reconstruct past atmospheres, measuring how much carbon dioxide, methane, and other gases floated above the Earth at different times. The patterns that emerge reveal more than just gentle ups and downs. During great cold snaps, the levels of greenhouse gases drop sharply, as if the planet's insulating blanket had thinned just when warmth was most needed. This fits with the idea of a world tipping toward deep cold. Fewer greenhouse gases mean less trapped heat, and less trapped heat allows ice to spread. Then there are fossils, the faint fingerprints of life. Even in rocks tied to intense glaciations, microfossils appear: tiny remains of simple organisms that manage to survive. They may have formed mats, filaments, or small colonies, clinging to existence in places where conditions were harsh and unforgiving. Their persistence hints at refuges, sheltered corners where life could endure even as the wider world froze. These refuges might have been near underwater hot springs, where hydrothermal vents on the ocean floor released warmth and a steady stream of minerals. They might have been in subglacial lakes, trapped beneath thick ice, kept liquid by pressure and geothermal heat. They could even have existed within the crust, in thin films of water around rocks, deep underground. Whatever their exact homes, these tiny survivors show how determined life can be, even when the surface story looks hopeless. Taken together, falling stones, ancient air, and stubborn microbes, each piece deepens our understanding of Earth's icy past. But knowing that the planet may have endured such a profound freeze only raises harder questions. What could push a living world so far into cold? And how did it ever come back? One obvious place to look is in the way Earth moves around the sunday. Over tens of thousands of years, the shape of our orbit and the tilt and wobble of our axis slowly change. These Milankovitch cycles alter how sunlight is spread over the globe, making some seasons milder or harsher and helping to pace ordinary ice ages. They play a real role in nudging climates toward glaciation or warmth. Yet, as strong as they are, these cycles are not enough on their own to explain a freeze that might last tens of millions of years. Their rhythms are too short. They can open the door to ice, but they do not keep it locked for such immense spans of time. Volcanic activity offers another possible trigger. Large eruptions can throw ash and tiny reflective particles high into the atmosphere, shading the surface and cooling the planet for years at a time. If many eruptions happen close together, the cooling can linger, but the effect of volcanic dust is usually temporary. Eventually, the particles fall out of the sky, and unless new eruptions reload the veil, the climate recovers. Volcanic winter can be sharp and severe, but it is not easily stretched into tens of millions of years. The carbon cycle is more promising as a long-term player. Carbon dioxide in the air helps keep Earth warm, and the balance between sources and sinks, volcanoes, oceans, rocks, plants, determines how thick that greenhouse blanket is. If something were to draw down carbon dioxide faster than it is replenished, the atmosphere could lose much of its ability to trap heat. In theory, this could help kickstart a deep freeze. But here, too, there is a limit. Over geologic time, processes like volcanic outgassing tend to restore carbon dioxide levels. Even if the cycle is disrupted, it is hard to keep it locked in a low state for tens of millions of years without some counteracting force eventually pushing it back. So each idea, orbital cycles, volcanoes, changes in the carbon cycle seems to explain part of the story, but not all of it. That has led many scientists to suspect that no single factor is enough. Instead, a combination of influences may have conspired. Small nudges from orbital changes, shifts in greenhouse gases, the arrangement of continents shaping ocean currents, perhaps even subtle variations in the sun's brightness. Together, they could have pushed Earth into a state that none of them could maintain alone. Among the theories that try to knit these clues together, the snowball Earth hypothesis stands out. In this vision, ice does not just grow thicker at the poles, it spreads relentlessly until almost the entire planet is locked in white. Oceans freeze at the surface, continents disappear beneath glacial sheets, and even equatorial waters are sealed under ice. The world's color changes. Dark oceans and green lands give way to a bright shell that reflects most incoming sunlight back into space. The mechanism behind this transformation is a feedback loop. As ice spreads, the planet's surface becomes more reflective, sending more of the sun's energy back into space. That extra reflection cools the climate further, allowing more ice to form. The more ice there is, the more cooling occurs, and so on. A relatively modest initial cooling, perhaps from a decrease in greenhouse gases, a slight drop in solar output, or a change in ocean circulation, could start the process. Once it begins, the feedback may drive the planet into a drastically colder state. Not everyone agrees that Earth ever became a complete snowball. Some researchers argue that if the freezing were absolute, life would have been pushed past its breaking point. Yet the fossil record says otherwise. To reconcile this, critics propose a slush ball scenario, where large parts of the planet are covered by thick ice, but narrow bands of open or thinly iced ocean remain, especially near the equator. These patches could have allowed sunlight to reach the water and supported some photosynthetic life, making survival easier. Supporters of the full snowball view reply that life did not need wide oceans of open water to persist. It could have taken shelter in those hidden warm spots, deep sea vents, subglacial lakes, warm fractures in the crust. In such places, heat and chemical energy come from within the Earth, not from sunlight. Microbial communities living there would barely notice what was happening at the surface. The debate continues, shaped by new measurements and models. But whatever the exact extent of the ice, one thing is clear: conditions were extraordinarily harsh. And instead of ending life, they seem to have tested it, sharpened it, and perhaps helped set the stage for later bursts of diversity. Microorganisms appear to have survived this long chill. Fossils from rocks associated with these glacial episodes show a surprising variety of forms for such extreme times. This hints that evolution did not simply pause, it adapted. Under intense pressure, organisms either found new ways to cope or vanished. In that crucible, new traits and strategies may have arisen, some of which would eventually be inherited by the lineages that lead to the species living today. How, in practical terms, did life endure? One gentle answer involves hydrothermal vents on the ocean floor. These deep oases, fed by the heat of Earth's interior, could have remained relatively stable even while the surface froze. There, chemistry and warmth are abundant, allowing microbes to feed on reactions between hot fluids and cold seawater. Subglacial lakes offer another refuge, bodies of liquid water trapped under thick ice, protected from the worst of the cold, and sometimes connected to deeper, warm water systems. Warm pockets within the crust, where groundwater circulates through hot rock, may have formed yet more bastions of habitability. In such niches, microbial life could persist in darkness, patiently outlasting the age of ice. Cells might enter dormant states, awaken when conditions allowed, and slowly replicate. Even if the global environment was hostile, these small, scattered sanctuaries would keep the thread of life from snapping. Eventually, after tens of millions of years, the freeze began to loosen. The question of how Earth thawed is as fascinating as how it froze. One leading idea centers again on greenhouse gases. Even during a snowball phase, volcanoes would continue to erupt, releasing carbon dioxide into the atmosphere. Under normal conditions, that gas would be balanced by processes like rock weathering, which removes carbon dioxide over time. But when the planet is covered in ice, many of those sinks shut down or weaken. There are fewer exposed rocks for rain to wash, and fewer active ecosystems to absorb carbon. If carbon dioxide continues to accumulate, while the usual removal mechanisms are muffled, its concentration in the atmosphere slowly rises. Over immense spans of time, this growing blanket of greenhouse gas traps more and more heat. At some tipping point, despite the bright, reflective ice, the planet begins to warm. Ice starts to thin, cracks open, and patches of darker ground or open water appear. Those darker surfaces absorb more sunlight than ice, adding to the warming. As the thaw accelerates, the oceans wake up, Water once locked beneath solid lids begins to circulate more freely, redistributing heat from equator to pole and from surface to depth. In this unfolding, ocean currents may have played a crucial role in redistributing heat. As the great sheets of ice began, very slowly, to loosen their grip, the oceans woke up. Places that had been locked beneath frozen lids started to open in patches, and the water underneath could move more freely again. Once currents were able to flow, they began to carry warmth from the equatorial regions toward the poles, the way a sleeping body slowly redistributes heat when it stirs. That motion did more than just mix temperatures. It helped accelerate the melting. Warmer water brushing the underside of the ice weakened it from below, making it easier for the frozen shell to thin, crack, and retreat. With the reawakening of the currents, Earth's climate system returned to something more dynamic. Heat was no longer trapped in isolated pockets. It could be transported, shifted, and shared between regions. That movement further destabilized the old ice regime. Instead of a quiet, rigid world capped in white, the planet edged back toward a state where winds, storms, and currents all interacted in a complex dance, continually reshaping the boundaries between ice, ocean, and air. Another gentle but important player in this thaw may have been the sun itself. Our star, though steady on human timescales, is not perfectly constant over cosmic stretches of time. Its energy output can vary, subtly but meaningfully. A period of increased solar activity, even a modest brightening, could supply just enough extra energy to nudge a frozen climate toward change. It does not take a dramatic surge, only a small increase in the average energy reaching Earth, enough to raise global temperatures by a few degrees, to begin shifting the balance. These small changes do not work alone. They can line up with natural variations in Earth's orbit and tilt the Milankovitch cycles, which already alter how sunlight is spread across the planet. When a slightly brighter sun, rising greenhouse gas levels, and orbital conditions that favor warming all coincide, their effects can add together. That synergy makes it easier for the climate to tip away from a stable snow-covered state. Once the ice retreats enough, another feedback begins to work in the opposite direction of the one that froze the world. A planet almost entirely wrapped in bright ice reflects a large fraction of incoming sunlight back into space. As the ice melts and darker surfaces appear, open ocean, bare rock, exposed soil, the overall reflectivity, or albedo, of Earth decreases. Darker surfaces absorb more energy. That extra absorption enhances the warming and speeds the thaw, allowing more ice to disappear and more dark surfaces to show. Slowly, the loop that once drove freezing now helps maintain a warmer world. The Great Thaw was probably not the result of a single switch flipping, but of many influences acting together. Greenhouse gases slowly accumulating from volcanic outgassing, ocean currents re-establishing their global circulation, and perhaps a slight rise in solar output. Together, they wrote a new chapter in Earth's story, turning the page from a nearly frozen past to a future where seas were open again and climates could support richer, more varied life at the surface. This long tale of freezing and thawing is not just a quiet curiosity about ancient times. It carries lessons for our present and for the future we are steadily creating. Today, we live in an era where climate is changing once more. But this time the main push is not a slow drift of continents or the gradual dimming and brightening of the Sunday. It is us. Human activity burning fossil fuels, altering forests, reshaping land, has raised greenhouse gas levels sharply in a very short span of time. By studying how Earth responded to extreme events in the deep past, we gain insight into how sensitive the climate system can be. The same basic levers that once helped the planet thaw, naturally greenhouse gases, ocean circulation, reflectivity, are still the ones we are nudging today, only much faster. Melting glaciers, rising sea levels, shifting rainfall patterns, and widespread wildfires are not just abstract data points. They are signs that the finely balanced engine of climate is being pushed out of its familiar range. We are not heading toward another snowball Earth. Our current path tilts in the opposite direction, but the comparison reminds us that large swings are possible, and that once certain thresholds are crossed, feedbacks can make changes difficult to reverse. The speed at which modern warming is happening is unprecedented in human history, and it invites us to look closely at what happens when the climate moves quickly from one state to another. At the same time, our technological abilities have given us new eyes. Satellites orbiting high above can track changes in ice cover, sea level, and atmospheric composition in real time. Space probes look back at Earth from afar, offering a cosmic vantage point on our glowing, fragile atmosphere. Sophisticated climate models, fueled by powerful computers, allow us to simulate past and future worlds, testing how different factors interact. These tools deepen our understanding, but technology also drives much of the energy use and resource extraction that are altering the climate in the first place. It is both lantern and fuel. The story of Earth's long freeze and gradual recovery can serve as a caution and a guide. By learning how the climate system behaved under extreme conditions, we better understand which levers matter most, how greenhouse gases, circulation patterns, and surface reflectivity shape the planet's temperature and weather. That knowledge is not just an academic comfort, it is a practical map, showing where small changes can lead to large consequences, and where careful choices might help steer us toward a more stable, livable future. If we pull back even farther, though, and look at Earth from the perspective of the wider universe, another layer of meaning appears. Our planet is just one tiny point of light in a galaxy filled with stars, and beyond that, a universe filled with countless galaxies. Yet Earth's climate history, with its swings between warmth and deep cold, offers one of the best case studies we have for how a habitable world can change over time. Each extreme helps us imagine what other planets might be like. In recent years, the study of exoplanets, worlds orbiting stars far beyond our sun, has blossomed. We have found planets scorched by intense radiation, worlds locked in perpetual day on one side and endless night on the other, giants made of gas, and small rocky spheres that might have oceans or thick atmospheres. Some of these climates, as far as we can infer, are far more extreme than anything Earth has ever experienced. By examining them, we refine our theories of what makes a planet warm or cold, stormy or calm, hospitable or hostile. When scientists build climate models for these distant worlds, they often start with what we have learned at home. Earth's own ice ages, snowball phases, and greenhouse episodes become test cases. If we can simulate our own history correctly, we gain confidence when we apply similar tools to planets many light years away. Every strange exoplanet we study, in turn, teaches us more about the range of possible climates and how life might respond to them. One of the quiet goals that threads through planetary science is the search for a true sibling to Earth, an Earth 2.0, orbiting another star. We imagine a rocky planet with liquid water at its surface and an atmosphere that can support stable temperatures over long times. Finding such a world would not just confirm that Earth is not unique, it would open new questions. Does that twin also undergo wild swings in climate? Could it experience its own versions of snowball episodes and great thaws? How would life there, if it exists, cope with those changes? Thinking about Earth's 100 million year freeze and about other planets' possible extremes pulls us into a broader meditation on the sustainability of life in the universe. If climates can swing so far, what does it take for life to persist through those swings? How often do planets cross thresholds that make complex life difficult or impossible? These questions do not yet have firm answers, but each new observation, each refined model, adds another brushstroke to the picture. The snowball Earth hypothesis, the orbital cycles, the role of volcanism, even subtle cosmic influences, all of these threads together form a multi-layered view of why our planet once froze so severely and how it thawed again. No single idea explains everything. Instead, we see an intricate interplay of forces, each one shifting the climate a little until the whole system settles into a new state. That complexity mirrors the complexity of our current moment, where many factors, natural and human, combine to shape the future of our world. And then, as our thoughts stretch outward, another kind of question appears, one less about climate and more about the civilizations that might inhabit other planets. If worlds can freeze and thaw, if life can endure and adapt, what happens when a species becomes so capable that it can reshape not just its own climate, but the way it draws energy from its star? Imagine a civilization so advanced that it no longer relies on the kind of modest power sources we use. No coal, no oil, no small solar panels scattered on rooftops, but instead reaches directly for the energy of its star. A physicist named Freeman Dyson once proposed a bold idea that such a civilization might eventually build enormous structures around its star, not as a solid shell, but as a vast swarm or network of collectors, capturing much of the star's light and converting it into usable energy. It is an audacious concept, but it rests on simple logic. As technology progresses, energy needs grow. The ultimate power source for any star-bound species is the star itself. Our own sun releases, in a single second, more energy than all of humanity has used throughout its history. To imagine a society capable of harvesting a significant fraction of that output is to imagine engineering on a scale that dwarfs planets. A Dyson-like structure, whether a swarm of satellites or something more continuous, would turn a star into a kind of vast power plant with almost unimaginable potential. It would change not only how that civilization lives, but also how the star appears to observers far away. From our distant vantage point, we would not see the fine details of such a structure. The star might look dimmer in visible light, because much of its energy would be intercepted. At the same time, the collected energy, once used and transformed, would eventually be released again as waste heat, likely in the infrared part of the spectrum. In other words, a star wrapped in advanced technology might glow strangely, less bright in some wavelengths, oddly strong in others. The idea is both thrilling and a little unsettling. While we are just learning to harness energy on a planetary scale, the possibility exists that somewhere, long before us, someone else may have learned to harness energy on a stellar scale. To search for such civilizations, astronomers look for unusual signals, especially in the infrared, where an excess of heat might betray engineering too large to hide. Recently, observations have revealed odd infrared behavior from 7 distant stars. Their light carries a faint strangeness, a glow that does not fit easily with ordinary stellar models. These anomalies have sparked careful debate and quiet excitement. Some wonder if we might, just possibly, be seeing the signatures of advanced technology, so-called techno-signatures. Others argue that there may be natural explanations we have not yet fully understood. Dust in unusual distributions, strange stages of stellar evolution, or other astrophysical processes. Either way, these peculiar infrared glows resist simple, familiar explanations. They hang in our data like gentle question marks. What is behind them? Are they whispers of extraterrestrial engineering? Or are they clues to new kinds of natural phenomena we have not yet learned to name? To rest a little more comfortably with the idea of Dyson spheres, it helps to place them on a kind of cosmic ladder of growth. One quiet way astronomers do this is with something called the Kardashev scale, a simple, almost storybook way of asking, how much energy can a civilization tap, and from where? In the mid-1960s, a Soviet astrophysicist named Nikolai Kardashev imagined three broad stages of technological development. A Type 1 civilization, in his picture, is one that has learned to use all the energy available on its home world. Not just a little sunshine and a few gusts of wind, but the full range: solar, wind, waves, rivers, geothermal heat from beneath the crust, perhaps even in the far future. The ability to tame the raw power of earthquakes and volcanoes instead of merely fearing them. A Type 1 species has, in effect, learned how to manage the energy budget of an entire planet. A Type 2 civilization stretches that reach outward. It does not stop at the ground under its feet. Instead, it turns toward its star and begins to collect energy directly from that blazing heart. This is where Dyson's idea slips gently into view. To move from Type 1 to Type 2, a civilization would need to surround its star with an enormous number of collectors or habitats, forming a loose, shimmering swarm that intercepts much of the outgoing light. In essence, the star becomes a power source, harnessed almost in full. Beyond even that, Kardashev imagined a Type 3 civilization, one so advanced that it can harvest and control the energy output of an entire galaxy. Not just one star, but billions. It is a level of power that is almost impossible for us to picture, like trying to imagine the weight of all the oceans held in your hands. Yet the idea is simple at its core. The more capable a civilization becomes, the more energy it is likely to use, and the farther it must reach to find it. The link between this scale and Dyson's spheres lies in that quiet connection between energy and progress. As societies grow, their tools and ambitions tend to demand more power. At some point, planetary resources alone may no longer be enough. Surrounding a star with collectors becomes not just a dream, but an almost logical next step in the long, slow climb up Kardashev's ladder. If such structures exist, the natural question is, how could we ever hope to find them from so far away? One of the gentlest yet most powerful ways is through infrared astronomy, a kind of night vision for the cosmos. While our eyes and traditional telescopes are tuned mostly to visible light, stars and dust and planets also shine in infrared wavelengths, the soft glow of warmth itself. By observing the sky in infrared, astronomers can see heat that ordinary optics miss, revealing cool objects, hidden structures, and subtle processes. Infrared astronomy began in a modest way in the mid-20th century, when early detectors were first pointed toward the heavens. Over time, these simple sensors gave way to dedicated space missions with finely tuned instruments. Space telescopes, such as the Wide Field Infrared Survey Explorer, often called WISE, and later observatories like the James Webb Space Telescope have transformed this field. Floating above Earth's atmosphere, they are not blinded by the infrared glow of air and water vapor. They can map the sky in long, gentle wavelengths with extraordinary sensitivity, picking up faint thermal signals from distant stars, galaxies, and dust clouds. This ability is crucial in the search for what are called technosignatures, possible signs of technology beyond Earth. Freeman Dyson's insight was that a civilization wrapping its star in collectors would change how that star looks. Visible light would be partially blocked, but the captured energy, once used, would eventually be radiated away again as waste heat. That heat would make the system glow unusually bright in the infrared. So instead of looking for strange radio messages or obvious constructions, Dyson suggested something quieter. Survey the sky in infrared and look for stars whose heat signature does not quite match what nature alone would produce. In this way, his idea became more than a thought experiment. It offered a method, a practical way to search. If we scan many stars and find some with excess infrared emission that cannot be easily explained by dust, youth, or ordinary stellar behavior, those stars might be candidates, places where something artificial could be at work. This line of thinking has guided several searches and has played a role in identifying stars whose infrared glow looks just a little out of place. Modern infrared surveys have opened this door wider. WISE, launched in the late 2000s, has mapped the entire sky in multiple infrared bands, cataloging hundreds of millions of objects. Its data, freely shared with the scientific community, has become a treasure trove for all sorts of questions: the distribution of asteroids, the structure of our galaxy, the nature of distant galaxies, and, tucked among them, the possibility of Dyson-like structures. By carefully measuring how much infrared light a star emits compared to what is expected for its type and temperature, astronomers can flag systems that seem to be radiating too much heat. One ambitious effort along these lines is a project devoted to combing through huge catalogs of stars in search of exactly this kind of anomaly. The team combines information from precise astrometric missions like Gaia, which tells us where stars are and how far away they lie, with near-infrared surveys such as the 2-micron all-sky survey and mid-infrared measurements from WISE. Together, these datasets allow them to build a detailed picture of each star's energy output across different wavelengths. To explore the possibility of Dyson spheres, the researchers construct theoretical models that describe how a star would appear if a portion of its light were captured and re-emitted as heat by a surrounding swarm of collectors. They then perform a systematic, or grid, search across a range of possible configurations and temperatures for such structures. For each star, they compare the observed infrared emission to what their models predict. Most stars behave as expected, their light matching natural patterns. A few, however, stand out. Using this careful, layered approach, the team has identified a small handful of intriguing candidates, about 7 objects that show an excess of infrared radiation not easily explained by routine astrophysical causes. Interestingly, all of these are associated with small, cool stars known as M-dwarfs. These stars are dimmer in visible light than a star like our Sun, which makes any additional infrared glow more noticeable. The fact that they are M-dwarfs does not prove anything about advanced engineering, but it does make the excess heat particularly interesting. The significance of this work lies not only in the specific candidates, but also in the method. It shows that long-standing astronomical datasets originally gathered for general surveys of the sky, can be re-examined with new questions in mind. By layering precise distances, multi-wavelength measurements, and physical models of hypothetical megastructures, we can quietly test the idea that some stars might be wrapped in technology. All of this is made far more powerful by recent advances in both instrumentation and data analysis. On the hardware side, improved detectors and systems like adaptive optics help sharpen our view, correcting for the blur introduced by Earth's atmosphere when we observe from the ground. Clearer images mean it is easier to separate faint infrared sources from background noise and to measure their properties accurately. On the software side, machine learning has become a kind of patient assistant, tirelessly combing through vast oceans of data. Instead of examining each star by hand, astronomers can train algorithms such as convolutional neural networks to recognize patterns in the combined measurements. These systems learn to distinguish ordinary stars, dusty disks, and other familiar infrared signatures from more unusual ones. In doing so, they can sift out false positives and highlight a small set of especially curious objects for closer study. In a sense, we are teaching our tools to be curious on our behalf. They scan the skies in infrared, compare what they see to what we expect, and gently flag anything that does not quite fit. These algorithms cannot tell us, on their own, whether a given signal truly comes from advanced engineering or from some natural phenomenon we have yet to understand. But they can identify the subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most quietly transformative tools in this search is the James Webb Space Telescope. Hanging far from Earth in the stillness of space, it looks out with eyes tuned especially to infrared light, and in doing so, it has already reshaped how we see the cosmos. Its primary mirror, made of many golden segments, gathers far more light than earlier infrared telescopes like WISE, and its sensitive instruments can pick up the faintest warmth from distant stars and galaxies, heat that would be invisible to ordinary optical telescopes. Webb is particularly powerful in the mid-infrared part of the spectrum, the very range where a Dyson-like structure would most likely glow. If a civilization were wrapping its star with collectors, much of the captured energy would eventually leak back out as waste heat, radiating at these wavelengths. In principle, that means a telescope like Webb could scan patches of sky and notice stars that seem oddly bright in the mid-infrared, their thermal signatures whispering that something unusual might be happening there. In practice, Webb's time is precious and carefully planned. Its schedule is filled months and years in advance, with observations of galaxies forming in the early universe, newborn stars wrapped in dust, exoplanet atmospheres, and countless other questions. There is only so much room to devote to hunting for Dyson spheres. Even so, whenever observations overlap with the right kinds of targets, the data can be revisited with this possibility in mind. Another layer of meaning hidden in the numbers. Alongside infrared light, radio waves carry their own quiet potential. Radio astronomy gives us another way to listen for technosignatures. Facilities like the Very Large Array in New Mexico, an arrangement of many dish antennas spread across the desert, can detect radio signals from across the universe. Natural objects produce radio emission all the time, but technology can too. In principle, a star-spanning structure that harvests huge amounts of energy might also give off radio noise as a byproduct. Communication systems, power transmission, or other processes we can barely imagine. Where infrared observations look for excess heat, Radio observatories can search for unusual patterns in the radio spectrum, signals that stand out from the soft hiss of natural processes. Used together, these approaches offer two complementary ways of probing the same deep question. If something as grand as a Dyson sphere existed, it might reveal itself not just in warmth, but in whispers of radio across the void. The work done by the Uppsala team, finding a handful of intriguing infrared candidates, is part of a growing pattern rather than a lone outlier. Another recent study took a similarly ambitious approach, but with a different slice of the stellar population. About 5 million main sequence stars of types similar to our Sun, known as F, G, and K stars. The researchers combined precise measurements from Gaia with near-infrared data and the mid-infrared observations from WISE, then used machine learning to predict how bright each star should appear in the infrared based on its other properties. When a star appeared significantly brighter in the mid-infrared than the model expected, it was flagged as unusual. From an initial sample of nearly 4.9 million objects, the analysis gradually narrowed the list down, applying additional filters to remove obvious false positives and known natural explanations. In the end, 53 stars remained, with clear, significant infrared excesses, 53 tiny question marks scattered through the sky. Some of these stars seem to have characteristics consistent with extreme debris disks, vast swarms of dust and rock left over from planetary formation, or perhaps stirred up by recent collisions. Such disks can glow brightly in the infrared, mimicking what a Dyson-like structure might look like. In one case, the star's age appears to be older than what standard models would expect for such a lively, dusty system, which in turn challenges our understanding of how long debris disks can persist or how they can be revived. It may hint at extended disk evolution or at processes not yet fully understood. The implications of these findings are both profound and delicate. If even one of these stars turned out to be surrounded by an artificial megastructure, it would be a direct sign that advanced civilizations exist elsewhere, a confirmation that we are not the first to reach for our star's power. But the scientific community moves carefully here. Dust clouds, debris disks, and other natural phenomena can create very similar infrared signatures. Until each candidate is examined with follow-up observations and more detailed modeling, the more cautious explanation is that nature is simply revealing new tricks. This caution is not skepticism for its own sake. It is a recognition of how hard the task really is. Many of these stars are thousands of light years away. Their light is faint, their signals easily blurred by distance and noise. Small errors in measuring their distance, their temperature, or the dust around them can lead to large uncertainties in interpreting their infrared excess. Some astronomers argue that our current understanding of how stars and planetary systems evolve is still incomplete, and that these anomalies may point to new astrophysical processes rather than to technology. While the search for Dyson spheres sits at the intersection of engineering dreams and observational astronomy, it is really part of a much larger tapestry, the search for life beyond Earth in all its possible forms. Scientists talk about two broad kinds of clues. Technosignatures are signs of technology, things like large-scale structures, unusual energy emissions, or patterns in radio waves that might indicate deliberate activity. Biosignatures are different. They are signs of biology itself, specific gases in a planet's atmosphere that are hard to produce without life, pigments on a surface, or patterns of light that suggest vegetation, oceans, or microbial mats at work. Some biosignatures are relatively simple to describe. Oxygen and methane, for example, are both gases that can be produced by life. When they coexist in certain ratios and conditions, they can signal ongoing biological activity because they tend to react with one another and do not usually stay in balance without a constant source. Other biosignatures might come from seasonal changes in a planet's spectrum or from very specific combinations of gases that chemistry alone is unlikely to maintain. Current and upcoming missions are quietly sharpening our ability to detect these subtle signs. The James Webb Space Telescope, with its infrared instruments, can watch as exoplanets pass in front of their stars, letting a little of the starlight filter through their atmospheres. By splitting that light into its component colors, Webb can reveal the fingerprints of different gases, hinting at whether an exoplanet's air is thick or thin, rich in water vapor, carbon dioxide, or other compounds. Even faint heat signatures can tell us about a planet's temperature, the presence of clouds, and its potential to host liquid water. The Transiting Exoplanet Survey Satellite, or TESS, plays a different but complementary role. TESS spends its time scanning wide swaths of the sky, watching for tiny dips in starlight that occur when planets pass in front of their stars. It has already identified thousands of exoplanet candidates, including many that orbit relatively nearby stars, making them prime targets for more detailed follow-up with Webb and other powerful telescopes. Together, TESS and Webb form a kind of relay. One finds planets, the other studies them in depth. Looking ahead, proposed missions with names like LUVOIR or HABEX, concepts of large ultraviolet, optical and infrared observatories, imagine telescopes capable of directly imaging Earth-like exoplanets. Instead of inferring a planet's presence from a transit, they would block out the star's light and take pictures of the planet itself, separating its faint glow from the blinding brightness next door. With such tools, we could study exoplanet atmospheres in exquisite detail, searching for both biosignatures and technosignatures with unprecedented clarity. On the ground, new giants are also taking shape. Telescopes like the extremely large telescope in Chile will use enormous mirrors and advanced optics to gather more light than any previous ground-based instrument. With their resolving power, they can help image exoplanets, map their atmospheres, and refine our understanding of distant worlds. The Square Kilometer Array, a vast radio observatory spread across continents, will listen to the universe at radio wavelengths with unmatched sensitivity, widening the search for natural and artificial radio sources. The quest is not limited to distant suns. Closer to home, scientists are also looking for life that might exist within our own solar system, hidden in places where sunlight is weak, but other forms of energy are available. Icy moons like Europa and Enceladus have already entered this story. Both host subsurface oceans, and both show signs that those oceans may be in contact with rocky seafloors. Missions such as Europa Clipper, already on its way, and possible future probes to Enceladus aim to taste the plumes, map the ice, and seek signs of microbial life in those dark, hidden waters. Each new telescope, each careful survey, each mission that dips a little closer to an ocean beneath ice adds another piece to the puzzle. Sometimes a discovery will turn out to be more ordinary than it first appeared. A dust cloud, a debris disk, a tricky bit of stellar physics. Sometimes it will reveal something genuinely new, expanding our sense of what planets and stars can do on their own. Either way, every step refines our view, tightening the focus on where and how to look. In this sense, the journey itself is as important as any final answer. The search for life and intelligence beyond Earth encourages us to deepen our understanding of physics, chemistry, geology, and biology all at once. It pushes us to build gentler, sharper instruments, to collaborate across continents, and to hold big questions in our minds for years at a time. Each innovation, each anomaly, each careful correction draws us a little closer to an answer that has lingered over humanity for as long as we have watched the stars. In the quiet of the night, when the sky feels particularly wide and the questions feel larger than we are, it often returns in the simplest possible form. Are we alone in the universe? When we ask whether we are alone, another quieter question often rises alongside it. What is this everything we are part of really made of? Imagine a theory so bold that it does not limit itself to one corner of physics, but reaches from the tiniest building blocks of matter to the largest structures in the cosmos. A theory that says the particles we talk about, electrons, quarks, photons, are not the most fundamental things after all, but notes in a deeper, unseen music. It even whispers that the three familiar directions of space might be just the visible tip of something much larger and hidden. But then imagine that this theory, despite all its mathematical grace, has never been seen directly in an experiment. No clear signal, no decisive measurement, just a long trail of equations and hints. For decades, some of the brightest minds have worked on it, argued over it, and still, it remains one of the most mysterious and controversial ideas in modern science. This is the strange, shimmering world of string theory, where hidden dimensions, unresolved paradoxes, and daring hopes about a theory of everything live side by side. The story, as it is usually told, begins quietly in the late 1960s. In the summer of 1968, at CERN, a young theoretical physicist named Gabriele Veneziano wrote a paper that he thought was about something fairly specific: the strong force, the interaction that holds the nuclei of atoms together. At that time, physicists were struggling to make sense of the zoo of particles discovered in accelerators and cosmic rays. They were looking for patterns, for models that could tame the chaos. Veneziano's paper, with its long and technical title, was a modest attempt to write down a formula that captured some of the puzzling behavior of strongly interacting particles. He did not set out to reinvent our understanding of reality, but his equation turned out to be strangely powerful. It seemed to solve several different problems at once, fitting scattering data in ways that surprised many people. When he returned from a short vacation, he found that colleagues were already excitedly discussing his result, sensing that something deep was hiding in the math. At first, no one, not even Veneziano, realized just how far those equations might reach. Over the next few years, other theorists, among them Leonard Susskind, Yoichiro Nambu, and Holger Nielsen, started to look at the formula from a different angle. Instead of treating it as just a clever trick for particle scattering, they asked, what kind of physical object could produce such a pattern naturally? The answer that slowly emerged was unexpected. The math looked as if it described not point-like particles at all, but one-dimensional objects, tiny strings that can vibrate. In this new picture, elementary particles are like different musical notes played by the same instrument. One mode of vibration might look to us like an electron, another like a quark, another like a particle carrying a force. Instead of many different ingredients, you have one fundamental entity, the string, and a rich variety of ways it can twist, oscillate, and fold. It was an elegant, almost poetic idea, but the early version of string theory ran into serious trouble. The theory had been built with the strong interaction in mind, which is a short-range force confining particles tightly. Yet the equations predicted massless states that would mediate a long-range force, something that did not fit with how the strong force actually behaves. On top of that, the theory seemed to require more spatial dimensions than the three we see. It was as if the math kept insisting that space had extra directions curled up somewhere, even though no experiment had hinted at such a thing. For many physicists, this was a step too far. During the 1970s, attention shifted elsewhere. A different framework, the Standard Model of particle physics, took shape and quickly proved its worth. It described three of the four known fundamental forces: electromagnetism, the weak force, and the strong force, with great success, using point-like particles in quantum fields, no strings required. Experiments kept confirming its predictions. Compared to that, string theory looked like a beautiful but misdirected attempt, clever but unnecessary. Still, the idea did not completely die. A small group of researchers, enchanted by the mathematical structure, continued to explore it. And as the Standard Model matured, its own limitations came into sharper focus. One of the biggest gaps was gravity. While general relativity describes gravity very well on large scales, it does not mesh neatly with quantum mechanics. Trying to quantize gravity using the same methods that work for the other forces leads to equations filled with infinities that are hard to tame. It is as though the two great pillars, quantum mechanics for the very small and general relativity for the very large, refuse to share the same foundation. Here, string theory quietly returned. Those massless states that once seemed like a problem could be reinterpreted. They looked very much like particles that carry gravity, called gravitons. And because strings are extended objects, not points, their interactions soften the infinities that plague point-particle approaches. In this light, string theory is not a failed model of the strong force, but a candidate for a unified framework in which quantum mechanics and gravity finally coexist without tearing the math apart. At its core, string theory starts from a simple, radical picture. The most fundamental ingredients of the universe are not dots, but tiny loops or segments of string. These strings are unimaginably small, far beyond the reach of any accelerator we can currently build. They can vibrate in different patterns, like a violin string can play many notes. Each distinct pattern of vibration corresponds to what we perceive as a different particle, with its own mass, charge, and spin. The forces of nature appear as particular modes of vibration. Matter particles are other modes. The universe becomes a kind of grand instrument, whose notes are particles, whose harmonies are forces. Because strings have size, however small, they smear out the interactions that would otherwise occur at a single point. This smoothing effect helps avoid some of the worst infinities that appear when you try to describe gravity in a quantum way. In the abstract, it offers a graceful merging of quantum field theory and general relativity, hinting that they might be two approximations of a deeper, string-based reality. But this grace comes with a price. For the equations to work consistently, they insist on more dimensions than the four we are used to, 3 of space and 1 of time. In many versions of string theory, the total count is 10, 1 time dimension and 9 spatial ones. Since we only experience 3 large spatial dimensions, the others must be hidden, tightly curled up into shapes so tiny that we cannot perceive them directly. These extra dimensions are not decorative. They shape how strings can vibrate. Their geometry influences which particles and forces are possible, like the shape of a room, affects which echoes can form. This leads to one of the more speculative and fascinating consequences, the idea of a multiverse. If extra dimensions can curl up in many different ways, then each distinct arrangement could lead to a different set of low-energy physics, different particle properties, different strengths of forces, perhaps even different values for basic constants. String theory does not seem to pick out one unique vacuum state. Instead, it may allow an enormous number of possible universes, each with its own physical laws. Our universe would then be one bubble in a much larger foam. Another central concept woven into many versions of string theory is supersymmetry. Supersymmetry proposes a deep symmetry between particles of matter and particles that carry forces. In a supersymmetric world, every known particle would have a heavier partner, called a superpartner. Fermions, matter particles, would be paired with bosons, force carriers, and vice versa. These partners would help cancel troublesome divergences in calculations and could explain why some forces behave the way they do, particularly at high energies. In the context of string theory, supersymmetry is not just an optional extra. It helps stabilize the theory and allows gravity to fit more naturally into the quantum picture. It smooths the mathematics and makes certain kinds of solutions possible. It also offers potential explanations for things like dark matter. Perhaps some of the superpartners could be invisible, stable particles that quietly fill space. The difficulty is that, so far, supersymmetry has not shown itself in our experiments. Powerful machines, like the Large Hadron Collider, have smashed particles together at high energies, searching for signs of superpartners, and have not yet found them. Likewise, no experiment has clearly revealed extra spatial dimensions. No detector has registered the telltale deviations from the standard model that string-inspired theories have hoped for. This brings us to the quiet tension at the heart of string theory. On one hand, it offers a remarkably rich and mathematically coherent framework. It unites gravity and quantum mechanics in a way that ordinary approaches struggle to match. It provides a language for talking about black holes, early universe cosmology, and even holographic principles, where a higher dimensional reality can be encoded on a lower dimensional surface. On the other hand, it has not made a crisp, unique prediction that experiments have been able to test and confirm. Compared to other theories in physics relativity, quantum electrodynamics, the standard model, which earned their status through repeated, precise experimental successes, string theory still stands in a more tentative place. Its intricate predictions about vibrating strings, hidden dimensions, supersymmetric partners, and vast landscapes of possible universes remain, for now, beyond direct observational reach. That absence of empirical evidence is the serious obstacle it cannot quite step around, at least, not yet. Unlike the great frameworks that have been anchored by measurements and experiments, string theory continues to live mostly in the realm of elegant possibility, waiting for the universe to whisper back an unmistakable yes. When you hold all of this in your mind, the boldness of string theory, its graceful equations, its silence in our detectors, it becomes clear that, for now, it lives more as a mathematical landscape than as a confirmed description of the world. It is beautiful, but beauty alone is not enough. Physics, in the end, has to touch reality. One of the most determined attempts to bring string theory down from the chalkboard and into the lab has taken place at the Large Hadron Collider, the vast ring of magnets buried under the countryside near Geneva. The LHC was built to explore the deepest layers of matter by smashing protons together at extraordinary energies, recreating for a brief moment conditions not so different from those just after the Big Bang. Among its many goals, One has been especially important for string theory: the search for supersymmetry. If supersymmetry is real, then every known particle, electrons, quarks, photons, and so on, should have a heavier partner, a kind of shadow twin. These superpartners would be a key pillar for many versions of string theory. Finding even one of them would be a strong hint that the stringy picture of the world is on the right track. So physicists sifted through mountains of collision data, looking for traces of particles that would not fit into the standard model, patterns of energy and momentum that might whisper, "Here I am something new." So far, the whispers have not come. Despite years of operation and many careful analyses, no clear superpartners have been seen. That absence does not prove that supersymmetry is false. Its particles might simply lie at energies beyond the LHC's reach, or show up in more subtle ways, but it does tighten the available space where the theory can comfortably live. For some researchers, this growing silence has deepened doubts. They worry that string theory may be more like an intricate piece of pure mathematics than a true map of the universe, especially because many of its key ideas, extra dimensions, certain types of supersymmetry, seem out of reach for present-day experiments. In science, testability is a kind of compass, a theory that cannot, even in principle, be checked against observation sits in an uneasy place. String theory's reliance on scales and dimensions far beyond our instruments pushes it toward that edge, and that has led some to ask with a quiet frown, will we ever be able to know if this is how nature truly works? Yet, even as direct experimental confirmation remains elusive, there have been moments that feel like the universe gently nodding. A few years ago, a group of physicists, Pedro Vieira, Andrea Guerrieri, João Penedones, and colleagues used a technique called the bootstrap to study quantum gravity in a controlled setting. Bootstrapping, in this context, means starting not from a detailed model, but from general principles, consistency, symmetry, and the known behavior of certain quantities. From those principles alone, you ask what must be true if the theory is not to tear itself apart. Working in a 10-dimensional, supersymmetric setup, they were able to compute a particular dimensionless number, often denoted by the Greek letter alpha, which measures the size of the first quantum correction to Einstein's equations of general relativity. In simpler words, it tells you how gravity begins to change once quantum effects are taken into account. Remarkably, the value they found matched exactly what string theory had long predicted for that same situation. This agreement does not prove that string theory is the one true theory of everything, but it is a striking hint that, at least in some corners, the string framework captures something real about quantum gravity. It is as if two very different paths, one starting from stringy vibrations, the other from abstract consistency requirements, met at the same quiet number. At the same time, advances in computation and machine learning have allowed theorists to probe another delicate part of string theory, the geometry of its hidden dimensions. In many models, these extra spatial directions are curled up into intricate shapes, known as Calabi-Yau manifolds. The precise shape of these manifolds controls which particles and forces appear in the low-energy world we can see, but calculating their detailed geometry is extremely hard, like trying to understand a many-folded origami sculpture from only a few shadowy projections. Physicists such as Fabien Rouet and collaborators have turned to neural networks to approximate these complicated geometries. By training algorithms on known examples, they teach the machines to predict key properties of the manifolds more quickly and accurately. With those approximations in hand, they can begin to estimate how different shapes of the extra dimensions might lead to different particle masses or interaction strengths. It is an early step, but an important one. A way of connecting the abstract curves and folds of higher dimensional spaces to numbers that, in principle, could someday be compared to experiment. Meanwhile, the debate around string theory has grown more intense and more philosophical. Supporters point to its rare ability to bring all the known forces, including gravity, under one mathematical roof. No other framework has managed such a unification with the same internal consistency. They argue that the lack of direct evidence is not a fatal flaw, but simply a sign of how deep into the foundations of reality this theory reaches. Perhaps, they suggest, we are like early astronomers with small telescopes, glimpsing hints of other worlds, but not yet able to see their details. Critics, on the other hand, worry that the focus on elegance and untestable mathematics leads physics away from its empirical roots. If a theory can be reshaped to accommodate almost any outcome, or if its key predictions all live forever beyond experimental reach, does it still count as physics in the usual sense? They caution that investing too heavily in such a framework might draw attention and resources away from ideas that are more tightly anchored to observation. This tension between the lure of mathematical beauty and the demand for experimental proof has turned string theory into a kind of mirror for deeper questions. Is a theory that explains much and predicts little still a physical theory, or has it become more like philosophy, written in equations, without clear tests? There is a worry that string theory might remain a grand, intricate game, impressive and inspiring, but never fully grounded in the world we can measure. Yet the story is not finished. New experimental techniques, more sensitive observations of the early universe, and creative uses of gravitational waves or tabletop experiments might someday probe aspects of quantum gravity indirectly. Some hope that hints of extra dimensions, subtle imprints in cosmological data, or new particles will eventually show up and nudge the balance. For now, though, the community remains divided, its hopes and doubts intertwined. Interestingly, one place where string theory has already offered deep insight, though again more on the conceptual side, is in our understanding of black holes. These dark, dense objects, born from the collapse of massive stars or from the slow feeding of matter into galactic centers, mark a frontier where our familiar laws of physics begin to fray. At their heart lies a puzzle that has troubled scientists for decades: the black hole information paradox. According to classical general relativity, when something falls into a black hole, it is gone for good. Not just the object itself, but all the detailed information about its internal state seems to vanish behind the event horizon, the boundary beyond which no signal can escape. From the outside, you are left with only a few simple numbers describing the black hole: its mass, its charge, its spin. Everything else is swallowed and hidden. Quantum mechanics, however, insists on a different rule. At its core is the idea that information is never truly destroyed. It can be scrambled, spread out, and made practically impossible to recover, but the underlying details are always preserved in the full wave function of the system. These two perspectives, relativity's vanishing act and quantum theory's strict bookkeeping, clash sharply in the context of black holes. String theory offers a more nuanced picture. Because strings and related objects, such as higher dimensional brains, can store information in many subtle ways, the theory suggests that the data about what falls into a black hole could be encoded in the microscopic structure of the black hole itself. Instead of a featureless classical object, a black hole becomes something with a rich internal makeup at the quantum level, built from countless stringy degrees of freedom that can remember, in principle, what has gone in. This idea is closely linked to another key piece of the puzzle: Hawking radiation. In the 1970s, Stephen Hawking showed that when you include quantum effects near the event horizon, black holes are not perfectly black at all. Particle-antiparticle pairs can flicker into existence near the horizon. One falls in while the other escapes, making it appear as if the black hole is emitting a faint glow. Over immense periods, this Hawking radiation causes the black hole to lose mass and, eventually, to evaporate entirely. In Hawking's original calculation, this radiation is purely thermal, like the featureless glow from a hot stove. It carries no imprint of the specific things that fell into the black hole. If that is exactly true, then when the black hole finally evaporates, all the detailed information about the objects it swallowed would seem to be gone from the universe forever. A direct contradiction to the principles of quantum mechanics. In the picture that string theory paints, the story of black holes does not end with information slipping away into silence. Instead, it suggests a softer, more careful possibility: that the radiation leaking from a black hole is not completely featureless after all. The idea is that the tiniest quantum ingredients, the microscopic degrees of freedom that make up a black hole in a stringy description, can store information about everything that has ever fallen in. As the black hole slowly emits Hawking radiation and shrinks, those hidden details are, in principle, woven into the outgoing particles. To us, that radiation would look almost perfectly thermal, like the warm breath of a slowly fading ember. Any pattern that carries information would be unimaginably subtle, scrambled and spread over vast timescales, but not truly absent. In this way, the principles of quantum mechanics, especially the rule that information is never truly destroyed, might be preserved. Even in the shadow of an evaporating black hole, the apparent paradox is softened into a puzzle about how information is encoded and revealed, rather than whether it survives at all. In this view, black holes are not just exotic astronomical curiosities. They become testbeds for ideas at the deepest levels of physics, where quantum mechanics and gravity must both be taken seriously. When string theory is applied to these objects, it bridges the microscopic world of quanta with the grand, curved space-time of general relativity. Black holes turn into laboratories, distant and dangerous, yes, but conceptually rich, where the micro and the macro meet. The insights that come from studying black holes this way have already led to remarkable connections, such as holographic principles that suggest information in a volume of space can be encoded on its boundary. They hint that our usual ways of thinking about space, time, and information may be only approximations to a deeper, more subtle structure. If those hints are right, understanding black holes through the lens of strings could eventually guide us toward a more complete picture of the universe's foundations, something closer to a unified story of all forces and particles. Even so, string theory does not walk alone. It shares the landscape of ideas with other ambitious approaches to quantum gravity. One of the most notable alternatives is loop quantum gravity. Instead of introducing tiny strings and extra dimensions, loop quantum gravity starts from a different intuition: that space and time themselves might be made of discrete units, like a woven fabric built from tiny loops. In this picture, space-time is not a perfectly smooth continuum, but a kind of quantum lattice at the smallest scales. Where string theory stretches into higher dimensions and vibrating objects, loop quantum gravity tries to quantize geometry directly, defining chunks of area and volume. Both frameworks reach for the same distant goal, a consistent quantum description of gravity, but they take very different paths. Their coexistence is a reminder that even among experts, there is no single agreed route forward. The search for a unified theory is not a straight line. It is more like a network of trails, some crossing, some diverging, all probing the fog. As these trails multiply, deeper questions begin to surface. They are not just technical questions about equations, but philosophical ones about what we can truly know. The work of Kurt Gödel, with his incompleteness theorems, drifts into the conversation. Gödel showed that in any sufficiently rich formal system, there are true statements that cannot be proven within that system itself. There are limits built into the very machinery of logic and proof. For some, this carries a haunting echo when we think about theories of everything. If our attempts to build a complete, self-consistent mathematical description of the universe are themselves subject to such limits, then perhaps no single theory can capture everything in a neat, closed form. String theory, with its ambitious scope and unresolved questions, sometimes feels like it is brushing up against this boundary, immense in reach, but always leaving open the possibility that some truths lie just beyond its horizon. The metaphor of an island of knowledge fits gently here. Picture human understanding as an island surrounded by a vast sea of the unknown. As science advances, the island grows new discoveries, expand the shoreline. New theories add land. But as the island spreads, so does its coastline, the boundary where knowledge meets mystery. The more we learn, the more we become aware of what we do not yet understand. String theory, with its higher dimensions, intricate geometries, and bold claims, pushes outward into that sea. It extends the island, but also lengthens the line where questions gather. This leads into a tension that has been quietly building in the scientific community. The pull between empirical science, rooted in observation and experiment, and theories driven primarily by mathematical structure. String theory is often placed in the middle of that tension. Its mathematics is rich and internally consistent, and many of its results connect beautifully to other areas of physics and pure math. Yet its direct, testable predictions remain distant. Critics worry that, without firm empirical anchors, string theory risks drifting into a kind of metaphysics, an elegant castle in the air whose relation to the physical world is unclear. They point out that science has always depended on the loop between theory and experiment. We propose, we test, we refine. If a framework cannot be tested, or if it can accommodate almost any outcome, they ask whether it still belongs in the same category as the great physical theories of the past. Defenders of string theory answer that many breakthroughs began in the realm of mathematics and only later found their observational confirmation. They like to recall how Einstein's general relativity was initially embraced not only for its bold predictions, but for the elegance of its equations, which seemed to capture gravity in a uniquely coherent way. Only afterwards did the bending of starlight during an eclipse and other tests confirm its truth. In their view, string theory is in a similar phase, a promising structure waiting for instruments subtle enough to probe it. Both perspectives carry a kind of truth. History does show that mathematical beauty can be a powerful guide. It also shows that not every beautiful idea survives contact with data. For string theory, the path forward depends heavily on whether new observational windows can be opened. More powerful particle accelerators could, in principle, reach energies where hints of stringy effects or supersymmetric partners begin to appear. Improved gravitational wave detectors might one day reveal subtle imprints of quantum gravity in the ripples of space-time. Precision observations of the early universe, black hole mergers, or high-energy cosmic events might carry faint messages from scales we cannot directly touch. Black holes and their quantum behavior remain especially promising. As we refine our understanding of Hawking radiation, as we gather more data on black hole mergers and the environments around them, we may find clues that support or challenge the string-based view of information and microstructure. The interplay between strings, horizons, and information flow is likely to remain a fertile ground where bits of theory and observation can meet. Looking ahead, it is clear that physicists do not yet agree on whether string theory will ultimately be the right description of reality's deepest layer. Some are cautiously optimistic, some are skeptical. Many are somewhere in between, appreciating both its achievements and its gaps. What almost everyone agrees on is that the search itself, the attempt to weave quantum mechanics, gravity, and all the forces together, is a powerful engine for creativity. It inspires new mathematics, new computational tools, new experiments, and new ways of seeing old problems. Whether the final answer turns out to be string theory, loop, quantum gravity, some synthesis of ideas, or something completely unexpected, the process of reaching toward it keeps enriching our understanding. The coming decades are likely to be especially important. As technology advances and new observatories and experiments come online, we will be able to test aspects of the universe that are, for now, only imagined. Until those tests speak clearly, we are left in a kind of thoughtful twilight, aware of how much we do not know, but also surrounded by hints and possibilities. Step by slow step, new discoveries and quiet breakthroughs will arrive, each one reshaping our view just a little. And somewhere along that path, they will help refine or replace the stories we tell about strings, space, time, and the deep workings of the cosmos that cradle us.